Warm greetings to all those who are listening in to this program. The South African Mathematics Foundation administers a number of mathematics Olympiad competitions, mathematics competitions throughout the year. Amongst them are the Junior South African Maths Olympiad and the Senior, which run over 3 rounds each. In addition to that, they administer the team competition, which attracts not only people from South Africa, but from elsewhere as well. In these team competitions, an average of 50 or more teams participate, teams of 10. The teams write 2 papers. One is an individual paper, where the contestants or the participants write on their own, and then there is another team paper where they club together in a group of 10 and try to solve 10 problems. The individual problems contain 15 questions. Today, we are in the process of unpacking all these competitions to give you some idea as to what the solutions to the problems are, all via Zoom presentations. Today, we are going to look at the 2024 Senior Individual paper, which was set in 2004. So with those few words, we will go straight to the matter at hand. Okay, so as you can see, we are doing the team. Senior individuals, which was set in 2024. Okay, let's look at the very first question. The first question says, the mass of a container half filled with liquid is 32 grams, 32 kgs. All right, so you have a container which is half filled, and the mass of it is 32 grams. Okay, when the container is filled to 3/4, it says that the mass is now 45 grams. So when it's half full, it's 3/4 full. So here, in this case, it is 35, 32 at least, 32 kg. And here it's 45 kg. And the question is, find the mass in kilograms of the empty container. Okay, so let's give it a name. Mass of empty container. We'll call it C for container. And of course, the liquid will give it a mass as well. Let's call the full tank liquid, or full container. Liquid, we'll call it L for liquid. So what do we have here? Here we have the mass, we have the container together with the liquid. So you got C. The liquid is only half full, and there you're given that is 32 kilograms. When you take the container and fill it with 3/4, liquid, you get C plus 3/4 L is 45. And the problem is to find C, mass of the container. Well, you can eliminate C very quickly here by subtracting. It's better to subtract from the first from the second, because then you got 3/4 minus half. We don't want negatives. So 3/4 minus half is 1/4 L. Well, L should not be confused with liters. It's liquid, L for liquid, or the full tank of liquid. And 42 minus 32 is 13. So if 1/4 of L is 13, L will have to be equal to 52. So we really need C. So C plus, according to the first equation, C plus half L, 1/2 of 52 is 26, is equal to 32. So that implies C is equal to 6. It has to be 6 kgs. But must always add the units. That is the mass of the container. All right. I always give the solutions to every problem as well. And you can see here I give a different kind of a solution which still comes to 6 kgs without any equations. Study that. That looks like an interesting solution. Okay, let's get on to the second question. The second question reads, all the natural numbers, you can count them, 1 to 8, and then we have 9 to 16, and so on. They are all listed in this table. The a 3 by 3 box is drawn around any 9 numbers as shown. You can see we marked them in yellow. 3 by 3. The sum of the numbers in another similar box, not shown here, is 639. Find the number in the top left corner of this box. Okay, so let's just examine this 3 by 3 box. When you work out the sum of those 9 numbers, it actually turns out to be 117. So the sum of these 9 numbers in the diagram is 117. You can check it out, which is actually equal to 9 times 13. So this 13 here is just the average of the 9 numbers. So the middle number is the average of the 9 numbers. It always is like that, because as you can see, if you look at the top row, 5 is the average of 6 and 10, 13 is the average of 12 and 14, 21 is the average of 20 and 22. So if you add all of them, you're going to get the middle. Okay, so the same thing happens with this block which we can't see. They say that the sum is 639. The sum is 639. So it means that the average of those 9 numbers must be 639 over 9. 639 divided by 9. And that is 71. So the average is sitting in the middle here. Right. Now the question is, what is the number in the top left corner? Top left corner is this one here. Well, if you look at the way it works here, 13, and so this has to be 17, 70. It's going increasing order. And then downwards, you can see 2 plus 8, 3 plus 8, 4 plus 8. So you keep adding 8. So this has to be 62. It has to be 70 minus 8. So the answer to our question is 62. Okay, so that takes care of question 2. And let's have a look at what the solution was that I worked out in advance. And this is done a little bit differently. Okay, I got another alternative as well. As you can see, because horizontally they increase by 1 and vertically they increase by 8. So if you call the very top number A, then you can find all the numbers in terms of A, and then you can add them to get 639 and get A, which is your top left number. All right, so that's another way of doing it. But I think my way is much more elegant. All right, so the next question is question 3. How many squares of all sizes are there in the figure below? Okay, you see lots of squares already, but these are the 1 by 1 squares. But we can count the 1 by 1 squares. Oh. The 1 by 1 squares, how many are there? You've got 4 at the top. Here you got 6 4s are 24. And you got 2 4s are 8 there. So it's 24 plus 8 is 32. All right, so you also got 2 by 2 squares. And to count the 2 by 2 squares can be quite difficult, but we can look at the centers. See, this is the center of the square here. See, this is the center. So we'll just count this, we'll identify the centers. This is another center, that's another center. That's not a center. But the only centers are these. These are all centers of the squares, centers of 2 by 2 squares. Oh yes, this is the one here as well. So these are the different centers. And I think, yeah, even these, okay, so you can see what the centers are. You got 3 5s in the middle, that's 15, and another 6 at the top and the bottom. So that gives you 21 2 by 2 squares. Right. So I like to count these in terms of the centers, then you can keep good track of it. So let's have a look at the 3 by 3 squares. Again, if you look at the centers of the 3 by 3 squares, if you look at the top one, the very first one, this is the first 3 by 3 square that you've got. And this is the center. Okay, so that's 1 3 by 3, and the next 3 by 3, this is the center. Okay, then you don't have, yeah, at the bottom here, you got that, and that are all centers of 3 by 3 squares. And even these two, you can actually check what they are, but these don't qualify. Oh, but wait a minute. This does qualify. This one and this one. Yeah. So here you can see what the centers are. You get 4, 8, 12. So there are 12, 3 by 3 squares. And then the 4 by 4 squares. Well, one of the things I notice is that when you count the 4 by 4 squares, you got 4 here. So these, that, that, that. So you can have this as the center. See? This is the center of this 4 by 4 square here. Right, so that's one of the centers. Likewise, this flank here gives you one square. That one there gives you another one. This one here gives another one. And this gives another one. So there are 4 already, like this one. And in addition to this, these 4, you have another one in the middle. And that is this one here. There's only one in the middle. Like that. You see this 4 by 4 square. So there are 5 altogether. The 5 4 by 4 squares. Okay. All right. So how many are there altogether? 53, 65, 70. So there are actually 70 squares. It doesn't look like it, but there are 70 squares in this picture of all different sizes. Let's just check our answer. As I said, I've worked these problems beforehand, and you can see the answer right at the bottom is saying 70. And I think they count the same way that we counted. All right, so let's go ahead with the next problem, which happens to be question 4, I think. Or is it question 5? It's question 4. Okay. So question 4, I have to tell you that this is a problem that requires a little bit of extra knowledge about numbers. See, let me just look at the different values for m. The question is, how many integer solutions does this equation have? So if we look at the integers, obviously negative integers wouldn't work here. Negative integers will give you fractions. All right, so you can start with m equals 0. M equals 0, this gives you 1. And then you're 1 minus 7. No, it doesn't work. So m is not equal to 0. And if you put 1, then minus 7, 2 minus 7 is still negative. It doesn't work. You put 2, it's still negative. 4 minus 7. But m equals 3 does work. For m equals 3, then you have 3 to the m is equal to 2 cubed minus 7. And that's equal to 1. 8 minus 7 is 1. And n equals 0 is an integer. They ask for integer solutions. So n equals 0 is a solution. So one of the solutions is mn equal to 3, 0. So this gives you one of the solutions. Okay, so we can assume that m is at least 4. I'm going to prove that it's greater or equal to 4. That there's only one solution if m is greater or equal to 4. Okay, now to do that, we have to go through this process. The first case, 3 to the power of n is equal to 2 to the power of m minus 7. Now, this object here is somewhat familiar. See, it should be well known that when you add all the powers of 2, say 1 plus 2 plus 2 squared up to 2 cubed, 2 to the power of, say, m minus 1. There are m terms here. This is a geometric series, right, with a common ratio 2. You can notice that each term is obtained from the previous one by multiplying by 2. So therefore, by definition, it's a geometric series, common ratio 2. And this is the sum of m terms, because you got starting from 1 here, 1 to m minus 1. But then m minus 1, you had to add one more to get m terms. So this is the sum of m terms of a geometric series. And you got a formula for that. A r to the power of n minus r minus 1. Okay. Now, what is a here? A is the first term. Your common ratio is 2. N represents the number of terms, and we said it's m minus 1 and over 2 minus 1. So this gives you 2 to the power of m minus 1. Now, let's rewrite this 3 to the n is equal to 2 cubed minus 7. No, I'm taking the general thing now. 2 to the m minus 7 at the bottom one here. And let me separate the 2 to the m minus 1. See, the idea is I want to show that both n and m are even numbers. Right? I want to show that. Here you can see, if m is even, or let's look at it like this. If m is odd, you rather say if m is odd, then what do you have? You have that you got an odd number of terms here, right? Maybe 15 or 17 or whatever. And what I'm going to do is I'm going to separate, I'm going to put them in pairs. Put 1 plus 2. The next one is 2 squared plus 2 cubed. Write it like that. And the next one is, this is 2 squared plus 2 cubed. The next one is 2 to the 4th into 1 plus 2. So now you see, I've got 2 here, 2 here, 2 here. I've taken care of 6 terms, but m is odd. So you're going to land up with a pair at the end plus 2 to the power of m minus 1. The last term. Right? Because this is the odd number of terms here. Now, why did I do all this? The reason is I can see that you can take out the powers of 2 in 2 consecutive terms, and you always get 3. So what you have here is, to go back to this equation here, your 3 to the n is equal to 2 to the power of m minus 1. Now here, this is a multiple of 3, multiple of 3, multiple of 3. Every bracket is a multiple of 3. So it's of the form 3a plus 2 to the power of m minus 1. Because you got all multiples of 3 up to this point. And the last term is isolated. Right? Now you can see, if m is at least 4, then n is at least 2. Now, by the way, if m equals 4, oh, okay, whatever, you could, if m is equal to 4, then you got 16 minus 7 is 9. So 3 to the n is more than 1. So this n is greater than 1. So 3 certainly is a factor of the left-hand side, and therefore 3 is a factor of the right-hand side. So 3 is already a factor of this. So 3 is a factor of, you write a factor of as a vertical line like this. Right? A vertical line B means A is a factor of B. It's a nice short way of writing factors. Now, this is impossible because a power of 2, 3 cannot be, which is impossible. And the reason why it's impossible is because we made the assumption that m is odd. So m is not odd. There are only 2 possibilities. So m is even. So this is very, very important. We'll come to the conclusion that this over here, m, is even. All right, I'm going to take all these things off to create some space. I'm going to now show that n is also even. N, remember, is the exponent of 3 in that equation. 3 to the n is equal to 2m minus 7. So 2 to the power of m minus 7. So we have that m is even. Now let's have a look at 3 to the power of n. Now there's an interesting thing you can notice is, if you take the powers of 3, the powers of 3, n equals 0, it's 1. 3 to the 1, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, and so on. Divide by 4. If you divide all these powers by 4 and look at remainders, if you divide them 4 and just look at what the remainder is, then you will see the following. Remainders are right. Let's have a look at this. Here the remainder is 1. Here it's 3. Here 4 2 is 8. Remainder 1. Here 4 6 is 24. Remainder is 3. This is 4 20s. Remainder 1. So you'll see the remainder is either 1 or 3. Right? And if n is even, this is 3 squared, 3 to the 4th. If n is even, three to the n is equal to 4n plus 1. It's dividing by 4, so it's a multiple of 4 plus 1. This is 3 squared, n is even. 3 to the 4th, n is even. And if n is odd, 3 to the n is equal to 4n plus 3. Right? You can actually prove this, but we're not going to. I'm not going to do that. You can just see the pattern. Okay, so we are looking at. So suppose, again, as we saw before, suppose n is odd. I'm going to come to a contradiction again. So you got 2 to the power of m minus 7 is equal to 3 to the power of n. And if n is odd, we just saw it's of the form. We shouldn't put 4n here. We should make it 4. No, we shouldn't even use m. So we'll use it 4k. 4k plus 1. All right? The n is already there. So you got 3 to the n is 4k plus 1 minus 7. No. What am I doing? Sorry. It's so 2 to the m minus 7 is 3 to the n, 3 to the power of n. And we saw that if n is odd, it's 4k plus 3. Sorry, not concentrating. It's because it's 1.5 hours to New Year's Eve. So you go 4k plus 3, right? Now, if you make 2 to the power of m your subject here, you'll get 4k plus 3 plus 7, which is 4k plus 10. And that's 4k plus 10. If you take out 2, you get that. Now, remember, m is greater or equal to 4. And here, this is 2 times an odd number. This is an even number plus 5. 2 times an odd number. And you can't have that because m is, it's like 16, 32, and so on. You got 2 times a power of 2. That's not odd. So this is, again, this is a contradiction. This is impossible. So once again, we can assume, we can conclude that our supposition is false. This is false now. It means that n is even. So we proved that both m and n are even. Right. I'm going to just remove all this. So if both m and n are even, I can write m as 2 times something, 2 times an integer. And the same with n. I'm going to now write m and n, both of which are even, as 2 times an integer. You'll have to give names to these integers. We'll call them, say, s and t. Right. Okay. So we can say that so M is even, it's 2s, and N is also even, 2t for positive integers, S and T. S and T are positive integers. All right, so where do we go from there? What I'm going to do is I'm going to make 7 the subject of this formula. Yeah, so that'll be 2 to the power of m minus 3 to the power of n, right? And we just saw that this is 2 to the 2s. So the exponent m is 2s minus 3, and this exponent is 2t. Now we can write this as 2 to the s all squared. That's the nice thing about getting even exponents, because they are squares now. But now you have a difference of 2 squares, you see. So this is 2 to the s minus 3 to the power of t into 2 to the s plus 3 to the power of t. Difference of 2 squares. You can factorize. But here you got 7 is a prime number. You got a prime number which is being factorized. Now this is not a contradiction. That is possible. It means that the smaller number is 1 and the larger number is 7. Right? That's the only factorization for 7. So you got these two equations. 2 to the s minus 3 to the power of t is 1. 2 to the s plus 3 to the t is 7. So if you add these, you'll get the minus 3 to the t plus 3 to the t cancels out. So you get twice 2 to the power of s, because you get 2 to the power of s plus 2 to the power of s. And that's 1 plus 7 is 8. Right. Now this is 2 to the power of s plus 1 on the left-hand side. And this is 2 cubed on this side. So now we get only one value for s, you see? Only one value for s. Right. So amongst all these infinitely valued values for m, there's only one m which will work. And if s is 2, that m is 2s. It's 4. So m is equal to 4. Right. And that's the only solution. Well, of course, we also had this as a solution. Let me just... So now you've got one other solution. M equals 4. Mn. Just like that, we now write down 4. M is equal to 4. And when you substitute m is equal to 4, you get, let's go to this. 2 to the power of 4 is 16. Minus 7 is 9. 3 to the n is 9. So therefore, n must be 2. So this, there are only 2 solutions. Exactly 2 solutions. All right, so that takes care of this problem here, which is question 4. I hope you learned a few things here. A couple of things we saw is we use the geometric series and the formula for that. Yeah, and the rest of it is somewhat obvious, but this business of pairing off and so on, it's all part of the mathematical tricks. See, the 2 to the power of m minus 1 is always a multiple of 3 if m is even. You see, you can actually try this out by doing the following. You can just experiment. What are the powers of 2? 2 to the 0 is 1. Right? Okay, you got 2, 4, 8, 16, 32, 64, and so on. Now you subtract 1, that's 0, 1, 3, 7, 9, 31, 63, and so on. So this is 2 to the m, and this is 2 to the m minus 1. Subtract 1. Now you'll notice 3, 9, 63. Notice that these all alternate numbers are multiples of 3. See? And the powers of 2, this is 2 squared. The m is 2 here. M is 2. Here, the 2 to the power of 4. Here, 2 to the power of 6. So when m is even, you have the 2 to the m minus 1 is a multiple of 3. But the point is that this thing you're only checking it out for 3 numbers. You don't know whether that pattern is going to continue. But it's an observation, right? And then you say, okay, suppose m is even, would I always get this a multiple of 3? And that is when the pairing takes place. You see what we did? We put brackets around 2 consecutive powers, and we saw that it's always a multiple of 3. So that proof is general. It's not just to illustrate with a few examples here, like the way we have done. And this, it's an observation, right? And after that, we prove things. Right? So you notice that this is true. Then you ask yourself, is this always true? Okay, so that takes care of that. And as I said, you see, I worked it out. And you can see right at the bottom, there are only 2 solutions. You can read this one. This solution is different from the one that I said. But it's a little bit more comprehensive. I just said that 3 to the power of n is 4n plus 1, 4k plus 1. I didn't prove it. Yeah, we actually prove it. So it's good for you to have a look at this. Y is 3 to the n plus 1 minus 3 to the n always leaves a remainder of 1 when you divide by 4. Okay, the next problem is question 5. 2 distinct real numbers, a and b, satisfy this. What is the value of ab? So you have an equation involving 2 unknowns. And you ask what is the value of AB. Okay, you're not asked to calculate A and calculate B, but you want to know what is A times B. All right. Now, I just want to notice here that you got square root of AB. So AB, for this to have any meaning, AB is greater or equal to 0. Because of the square root. Now, let's see, is AB equal to 0? Well, if so, if AB is equal to 0, then one of them is 0. Either A or B is 0. So we can say, assume that say A is 0. That AB equal to 0. Now we try to solve for B. A is equal to 0, you got 1 there, 1 over 1. You got 1 over 1 plus B. And A is equal to 0, so that part there becomes 0. So you have 2. 2 over 1, which is 2. So you have 1 over 1 plus B is equal to 2 minus 1. Turn them around, you get B plus 1 is equal to 1. And you get B equals 0. So if A equals 0, then B is also equal to 0. And that's not allowed because they say they are distinct. Right? So, but A and B must be distinct. So what we're going to assume now that is that AB is not 0, that is AB is positive, strictly greater than 0. Now this means that either A and B are both 0, are both positive, or both are negative. The product of two numbers being positive means that either both are positive or both are negative. So we're going to just consider the two cases. Consider the case A greater than 0 and B greater than 0. Now, but you see, I got square root of AB here. That's why I'm going in this direction. Because square root, I can't work with square roots. Right? But I know if they are real numbers and A is a positive number, A certainly has got a square root. So let A be equal to x squared. A is a positive number, it has to be the square of some positive number, and B is also a square. Every positive number is a square. Now we are talking about real numbers here, you see, not integers anymore. So every positive real number is a square of some real number. It's got a square root, in other words. We're calling x the square root. All right, so once we got that, and here we can choose y to be positive. All right, so now our equation now becomes 1 over 1 plus x squared. I'm looking at that equation there. Plus 1 over 1 plus y squared equals 2 over 1 plus the square root of AB is square root of x squared y squared. The square root of x squared y squared is xy. Actually, that is not true. The square root of m squared is not necessarily m. It's m or minus m. But you will say, but wait a minute. When you got square root sign, you have to take the positive square root. Yeah, that's true. You have to take the positive square root. But you don't know whether m is positive or negative. So if m is negative, you have to take that square root. If m is positive, you take that one. Right? So if this quantity is negative, you'll have to take the negative square root. See? But if that quantity m is positive, then you have to take the positive square root. So here, this square root of x squared y squared, this xy is positive, you see, because we said we're choosing x and y to be positive here. So that is why I don't have to put a minus sign here. I'll have to put plus xy. because xy is by assumption positive. All right, now here you have to multiply, right? Well, let's do it like this. You've got a common denominator. On the left-hand side, what have you got? You got 1 plus x squared times 1 plus y squared. And the numerator is 1 plus y squared plus 1 plus x squared. Sorry, it's somewhat cramped here. And this is 2 over 1 plus xy. So if you cross multiply, you'll have 1 plus xy. The numerator is 2 plus x squared plus y squared. 1 plus 1 is 2. And I'm putting the others like that. And on this side, you got 2 into 1 plus x squared into 1 plus y squared. It's looking rather frightening, but if you plot along, you see there is a light at the end of the tunnel. So you got 1 plus xy. I'm going to multiply every one of these by 1 plus xy. Right? So starting with 2 is 2 plus 2xy plus x squared. And if you multiply this by x squared, you get x squared plus x cubed y. And then you take y squared and multiply these two by y squared, you get plus y squared plus xy cubed. Right? So that is on the left-hand side. And on the right-hand side, you have, now I'm going to, so 1 times 1 is 1. So I'm going to multiply it by 2 at the same time. The middle term is x squared. Multiply by 2, you get 2x squared. The flanks is 1 times y squared. Multiply that by 2, you get 2y squared. And then the last terms are x squared, y squared. Multiply that by 2. Right, so where does that get us? I'm going to cancel, I'm going to bring all the terms to one side. Right. Now, let's start with this. 2's on either side of the equation. Okay, we can cancel them. You got x squared here, and you got a 2x squared. Yeah. I didn't want to cancel this 2 here. Sorry about that. This is the 2. So you got 2x squared on the right-hand side and x squared on the left-hand side. I'm going to bring everything to the right-hand side. So you get 2x squared minus x squared is x squared. And then you got 2y squared on this side, and I got a y squared on the other side. So I got plus y squared. Right? So on the left-hand side, what have I got? I got a 2xy. And let's take that out. And then I got plus x cubed y. Let's take that out. No, wait a minute. I must take this to the other side. Sorry. I'm taking the 2xy to the other side, so the sign changes. So it's minus, and here you have minus x cubed y. X cubed y is on the left-hand side, and It's minus xy cubed. It's also on the left-hand side, but this one here is on the right-hand side. So I leave the sign intact. And all this is equal to 0. I'm bringing everything to the left, to the right-hand side. So you'll see all disappear. So you only have 0 here. So this is equal to 0. Now, when you look at these three terms, you'll notice that this is x minus y all squared. Right? X minus y squared is equal to that. Now here, I'm going to take out xy as a common factor. Minus xy. The x squared. Take out xy from here, you get plus y squared. I've got a minus sign in front. And here I got a plus sign in front. I have to put minus. That's 2xy. And all this is equal to 0. But watch, this is x minus y all squared. It's equal to 0. This is x minus y all squared. Same as that. Okay, so it's getting interesting. This left-hand side is actually factorizes. Because you can take out x minus y squared, x minus y all squared as a common factor, and the remaining factor is 1 minus xy. All right, so I'm going to write those factors like that. X minus y all squared is a common factor into 1 minus xy. Equals 0. Okay, so therefore it means that therefore x is equal to y or xy equals 1. Now this is not allowed because these numbers are distinct. See? So if x equals y, it means that a squared, x squared equals y squared. And this was a and this was b. So this is not allowed. So therefore, xy equals 1. Now, if xy is equal to 1, that means x squared y squared is equal to 1. Why do I do that? Because I need to find ab, you see. And a is x squared. So a is x squared. So if I square this on both sides, I have ab equals 1. So this is the question. Right? What is the value of ab? And the answer is that ab is actually equal to 1. See? Now, we still have to consider the other case where a is negative and b is negative. Now, that's quite frightening that we have to go through all that process. But unfortunately, you have to do it. And so I'm not going to do it. I've already given you the hint on how to proceed with this problem. But I can just tell you if a is negative and b is negative, what you can do is then you can say minus a is positive. And if it's positive, it's got a square root. Right? So you can write it as x squared and minus b, we call it something else. It's y squared. The same as before. But this time, minus a is x squared. Right? Or a is minus x squared. So here you will have 1 minus x squared, 1 minus y squared. And here with ab, the same as minus a times minus b. And the square root of ab the square root of xy all squared. But I can assume that x is positive here. Minus a is the square of a positive number. So xy, square root of xy squared is xy. So when you simplify this will lead to the following. a nice exercise for you. This leads to x plus y all squared into 1 minus xy. The same kind of a thing, but you got x plus y all squared. That's the only difference. So therefore, x equals negative y, or xy equals 1 in this case. But x equals negative y cannot hold because if x is negative y, then you'll still see that x squared is equal to y squared, and because you're squaring on both sides, and that will be a equals b. Because a was minus x squared, and b is minus y squared. And this is not on, because these numbers a and b are distinct. So this cannot work, and therefore xy equals 1 again, right? Which means that x squared y squared is equal to 1. That's minus a times minus b is equal to 1, because x squared is minus a, you see. And once again, you get ab equals 1. So even in the other case, you'll see if a and b are both negative, you'll still see that ab will still be equal to 1. So we always have the value of ab to be 1. Okay, so that's question 5. Oh, I left space for me to work. And this is the solution that I worked out. You'll see it's almost, I think it's almost exactly the same thing, but it's in a much neater form. All right, so that's question 5. Let's go to question 6. Question 6. It says that you've got a regular hexagon. It's a regular hexagon. In fact, the way we prove it, it need not be regular. But for the time being, we can say it's regular. It's got 2,024 points inside it. That's the year in which this problem was written. So sorry, my slide seems to have jumped here. All right, so you got over 2,000 points inside here, and they say that each. Well, I'm not going to go through this whole essay here. What's actually happening is that each of these points is connected to maybe another point like this, or to a point on the boundary, right? And you can have more than one connection. Like here, you got 3. 1, 2, 3, 4 connections, right? But the only condition is that this whole thing is broken up into pentagons and triangles. See? So you'll see that in this diagram here, a pentagon is a 5-sided figure. It need not be convex, could be concave. In other words, some of the interior angles is more than 180 degrees. So you'll see here, this is a pentagon. 1, 2, 3, 4, 5. And all these are all pentagons. And these two are triangles. So in this picture here, you see what the problem is. Now, the question is the following. How many, they call this pentagonal cells. can be at most in this partition. You can add, you can join them anyhow you like, but what is the largest number of pentagons you can construct? So the question is, what is the largest value of pentagons you can construct? So we'd better give a name to the number of pentagons. Let M equal to the number of pentagons after joining all these things. I don't know how you pronounce pentagon or pentagon. M equals number. So in this case here, M is equal to 4, for example. And let N equal to the number of triangles. So here, in this case, N is equal to 2. But this is only an illustration. We've got something which is very much more profound. You've got 2024 points inside here. And they all join together like this. You know, a frightening kind of array, which is impossible to imagine. And yet we are asked the question, what is the... So the question is, what is the largest value of M? M is the number of pentagons. So that is the question. Okay. What we do now is, there's a good strategy. And if you don't know how to do this thing here, it's very difficult to actually solve this problem. So the strategy is, sum all the angles in the figure, sum all the angles in the, you actually call it a partition. It has got 2024 points inside it in 2 different ways. Right. Now I'm going to do that in this special case. And I'll try to see how we can get an answer to this. Okay, suppose I take this point here. All the angles in the figure are, there are 2 here, and here there are 1, 2, 3, 4, and here there's a hell of a lot. So how do you sum all the angles? Well, one of the ways of doing it is look at each point and sum all the angles around it. So I'm going to sum those angles there, and I get, for this point, the sum of those angles is 360. Well, obviously, it's going to be 360 right throughout. Here you got 4 angles. They sum to 460. Here you got a sum of 3 angles. Oh no, actually 4 there too. That also adds up to 360. And here you got 360. So it takes care of all the angles inside there. So in this example here, you got 5 points. 1, 2, 3, 4, 5. You got 5 points. And at each of those points, the sum of the angles is 360 degrees. But then you also have these angles at the vertices are also the angles. See, we haven't included them. So you have to include all the angles at the vertices, which means it's the sum of all the interior angles of a hexagon, because those are the angles of the vertices. So the remaining angles are the sum of the interior angles of the hexagon. In any polygon having n sides, the sum of the interior angles of a polygon having n sides is a very simple formula. It's n minus 2 straight angles. By a straight angle, I mean 180 degrees. Right? So if you've got a polygon having n sides, you always have that no matter what the polygon looks like, you always have that if you add all the internal angles, you are going to get n minus 2 times 180 degrees. So yeah, you got 6. So 6 minus 2 times 180 degrees. Right? That's the sum of the angles of a hexagon. So this is 4. So this is how you calculate the sum of all these angles in one way. So if you watch this, it means the 5 represents the number of points inside, right? And this represents the points of the hexagon in the boundary. That doesn't change. But even in the 2024 cases, you still have got a hexagon in the background. Okay, so the only thing you have to do is that you don't have 5 points, you've got 2024 points. And each of those points, the angles add up to 360 degrees, plus you still got an hexagon in the boundary, and that is 720 degrees. That's 4 times 180. So you can see you 360 goes into this. So this is 360 degrees multiplied by the 2024 here, and there's 2 there. So it's 2026. All right, so this is one of the ways of adding all the angles in the picture. So this is the answer. But now there's another way of adding all these things. I promised you that we must find strategy, sum all the angles in the partition in 2 different ways. Okay, now I'm going to do it in the other way. So then I have an equation. Now what is the other way? The other way is you add all the angles in this pentagon. That includes that one there as well, right? And there are, all the pentagons have got 5 minus 2 straight angles. So that makes 540. So you add the angles of the pentagon here to its 540. Every pentagon, the interior angles add up to 540. And then you got 2 triangles. And the sum of the angles of the triangle is 180. You don't have to use n minus 2. N is 3. 3 minus 2 is 1. One straight angle is 180 degrees. So the triangle is a special case. Right. So what have you got? You got 4 540s and 2 triangles. Now observe that 4 is the number of pentagons. So you've got m pentagons. We chose the m to be the number of pentagons, and each pentagon is 540 degrees. So it's 540 times the number of pentagons. And the triangles, each triangle is 180. And there are n triangles. So when you work this out, you will get all the angles that you can see. The 540 represents the 5 angles side here. the 5 angles here, the 5 angles here, 5 angles here, the 3 angles inside there. And that way you exhaust all the possible angles you'll see in the picture. And we have already seen that this is also 360 times 2026. I don't like this time sign. I want to put it in brackets. My time sign looks like an X. 360 times 2026. You can cancel the 180. This is 180 times 3. The 180 times n. And this is 180 goes into this 2 times. 2 times 2000. So you get an equation involving m and n. Now that's quite remarkable. Where m is a number of pentagons and n is a number of triangles. So you can count the number of pentagons and the number of triangles. Very beautifully done. It's 3m plus n. Okay. Now I'm going to focus on this. Remember, we want to maximize m. Now you have to use a little bit of thinking here. To maximize m, that's the question. Find how many pentagonal can be at most in this partition. Oh, the word partition is mentioned. To maximize m, we minimize n. Because these two things add up to the same number. Minimize n. So let's start. The smallest value of n is 0. But then you got 3m, you got 4052. And 4052 is not a multiple of 3. Because when you add these, you get 11. And here you got a multiple of 3. So that doesn't work. N equals 1. Same story. 3m plus 1. N equals 1. It's 4050. 4052 again. But this time you have 3m equals 4051. And again, you got 4 plus 5 plus 1 is 10. Doesn't work. All right, so try n equals 2. N equals 2, just go back to this. You get 3m. Bring the 2 to the other side at 4050. 4052 minus 2. Right? I'm putting the n on the other side. And that's fine because this 4 plus 5 is 9. So 3m is equal to 1350. So you minimize m, so n, so we can go through the process and you'll see the first value of n, which produces a solution, is that. So this is the maximum. So your is maximum. So the answer is 1350. Ah, you can see at the last line. They look almost the same. But here, I don't know why we even included quadrilaterals. Maybe I didn't read the question carefully. So you got, we are saying that suppose there are quadrilaterals as well. And in practice, you're going to have triangles, quadrilaterals, and pentagons. It's quite difficult to draw it. Otherwise, they could have asked this question, which is far more meaningful, because then you you can join them without having to worry too much about whether you're including a quadrilateral figure. But even if you got quadrilaterals, you still get the same answer for the maximal number of pentagons.